This black hole fills more space than expected. Astronomers measure its mass from orbiting stars. It should be far smaller. Telescopes track stars whipping around an unseen center. Their paths curve sharply, as if pulled by something dense. Motion maps show speeds rising closer to the core. The mass grows with every new measurement, not by a little, by orders that should not exist. Nearby gas clouds stretch and glow as they fall inward. Their light reveals a boundary far wider than predicted. The event horizon spreads across a region it should not reach. Gravity should limit the size. Instead, it keeps expanding. Entire star clusters move as if bound to its pull. Then, distant regions of the galaxy begin to drift toward the same point. What began as a single object now dominates an entire galactic core. Something this large should not fit inside the laws that describe it. Astronomers first assumed a simple cause. A black hole grows by feeding slowly over time. But new measurements refuse that explanation. The mass did not build gradually. It appears already immense. The surrounding stars do not just orbit, they reorganize around it. This is not the growth of a single black hole. It is the reshaping of an entire galactic center. The galaxy appears first as a quiet system, a measured spread of stars held in a stable orbit. From a distance, it resembles countless others, a diffuse glow with a brighter center, nothing that demands special attention. Astronomers begin with light, mapping its distribution, measuring its velocity, tracing the motion of stars that circle the unseen core. At this scale, the system behaves normally. Stars move in predictable paths. Gravity holds structure together. Then the measurements tighten. Spectral lines shift, not slightly, but with a force that implies a deeper gravitational well. Stars near the center accelerate beyond expectation, their velocities climbing in a way that suggests a mass far greater than the visible structure can support. The first assumption is error. Instruments recalibrated, observations repeated, data compared across independent teams. The result does not change. At the center sits a black hole with a mass that exceeds the proportional limits defined by its host galaxy. Not by a small margin, but by a scale that forces reconsideration of the entire system. This is where the familiar category begins to fracture. Black holes at galactic centers are not unusual. They follow a pattern, a correlation between the mass of the black hole and the mass of the galaxy bulge that surrounds it. This relationship is not arbitrary. It emerges from a shared growth process. Gas falls inward, stars form, energy feeds back into the system, regulating both structures together. The black hole grows, but the galaxy responds. A balance forms. Here, that balance is gone. The galaxy is too light for what it contains. The central mass dominates beyond what the surrounding stars can justify. Gravity pulls inward. Imagine a star orbiting near the core. Its path tightens as it approaches, velocity increasing as the gravitational pull strengthens. But instead of encountering a gradual increase, the star enters a region where gravity rises sharply, as if stepping into a deeper basin than the galaxy should be able to create. The orbit curves more aggressively, the period shortens, energy redistributes through the system. This is not a subtle deviation. The black hole mass, when measured through stellar motion and gas dynamics, suggests a central object that outweighs expectations by several times. Not a rounding error, but a structural contradiction. And yet the galaxy itself shows no signs of having once been larger. Its star count, its distribution, its luminosity, all indicate a system that has always been modest in scale. There is no evidence of a massive past stripped away. No clear sign of collision, no tidal remnants, no extended halo that would hint at lost mass. The black hole did not inherit this size from a vanished galaxy. It exists here, now, inside a structure that cannot explain it. This forces a shift in how the system is seen. The galaxy is no longer the dominant frame. The black hole becomes the defining structure, the anchor around which everything else must be reconsidered. Stars are no longer the primary measure. They are tracers, moving indicators of a deeper gravitational architecture. Gas flows toward the center, drawn inward along curved paths, heating as it compresses. Radiation emerges from the inner region, not as a bright quasar, but as a controlled release of energy, a system active but not overwhelming. The black hole is present, but not violently consuming. This quiet state makes the contradiction sharper. If the black hole had grown rapidly through extreme accretion, the galaxy should show signs of disruption. Energy output at that scale would push gas outward, suppress star formation, alter the structure of the entire system. But the galaxy remains intact. Stars continue to orbit in ordered paths. Gas clouds persist, not fully expelled, not violently disturbed. The system appears calm, yet its central mass suggests a history of intense growth. This mismatch becomes the central tension. Either the black hole grew in a way that avoided disturbing its host, or the host failed to grow in response. Both possibilities challenge existing models. To understand this, the measurement must expand beyond the immediate system. Astronomers compare this galaxy to others, placing it within a broader population. They examine scaling relations, plotting black hole mass against stellar velocity dispersion, against bulge mass, against luminosity. This object falls far outside the expected line. It is not an outlier by chance. It represents a break in the pattern itself. The implication is not that one measurement is wrong. The implication is that the rule governing these systems may not be universal. This is where the object stops being just a black hole. It becomes a test of how galaxies and their central masses are connected. If the relationship can break here, it can break elsewhere. And if that connection is not fixed, then the growth of structure across the universe may follow paths that are less constrained than once believed. The galaxy no longer explains the black hole. The black hole begins to redefine the galaxy. The measurement begins with motion. Not light alone, but the way light shifts as stars move through space. Each star carries a signature, a spectrum stretched or compressed depending on its velocity. When these shifts are mapped across the inner region, a pattern emerges, a tightening spiral of speed around an invisible center. Velocity becomes evidence. Closer to the core, stars accelerate to thousands of kilometers each second. Their paths curve sharply, bound to a mass that cannot be seen, but can be calculated with precision. The numbers converge on a single conclusion. The central object contains billions of solar masses. This is where scale breaks again. For a galaxy of this size, the expected black hole mass should be far smaller. The proportional relationship has been tested across many systems, and it holds with surprising consistency. But here, the measured mass exceeds that expectation by a wide margin. The difference is not subtle. To understand what this means, the system must be translated into physical terms. Imagine compressing billions of suns into a region smaller than the orbit of our solar system. Gravity in this region does not behave gently. Space curves steeply. Light passing near the center bends, its path redirected, its frequency shifted. Time itself slows in the deep gravitational well, ticking differently for anything that moves too close. A disk of gas forms around the black hole, spiraling inward. Friction heats the material, raising temperatures to millions of degrees. Radiation emerges. But in this system, the emission is restrained. The accretion rate is moderate, the black hole active but not extreme. This creates a second contradiction. If the black hole is this massive, it must have grown through sustained inflow of matter. Gas falling inward, converting gravitational energy into radiation, shaping the surrounding galaxy. That process should leave traces. Outflows, shock waves, regions where star formation has been suppressed, signatures of feedback that ripple through the entire structure. Yet the galaxy does not display these scars at the expected scale. Its stars remain distributed in a relatively stable configuration. Its gas has not been entirely expelled. The system does not look like it has been dominated by a central engine of this magnitude. This forces a closer look at how the measurements are made. Astronomers refine their models, separating contributions from stars, gas, and dark matter. They isolate the gravitational influence of the central mass by subtracting everything else. What remains is consistent. The black hole is not an artifact of miscalculation. It is a real concentration of mass that defines the inner dynamics of the galaxy. A second method confirms it. Gas clouds orbiting near the center emit radiation at specific frequencies. These emissions shift as the clouds move, tracing precise circular paths. By measuring these motions, astronomers can calculate the enclosed mass directly. The result matches the stellar measurements. Two independent approaches converge on the same number. The mass is real. This convergence removes uncertainty and replaces it with pressure. If the measurement is correct, then the system itself must be reconsidered. The black hole is not just larger than expected, it dominates the gravitational structure far beyond the central region. Stars that appear distant from the core still feel its influence, their velocity shaped by a mass that extends its reach outward. The galaxy becomes a secondary structure. Its stars orbit not just within their own collective gravity, but within a field defined by the central black hole. This shifts the hierarchy. The black hole is no longer embedded within the galaxy. The galaxy is partially organized around the black hole. A quiet inversion begins to take shape. To visualize this, imagine a system where the central mass sets the rhythm of motion across vast distances. Stars respond to a gravitational command that originates from a single point. Their orbits align with a deeper potential, one that the visible structure alone cannot generate. This is not how most galaxies behave. In typical systems, the combined mass of stars dominates the gravitational field at large scales. The black hole influences only the inner region. Here, that boundary blurs. The influence of the black hole extends further than expected, reshaping the velocity field of the galaxy itself. This is where the scale correction becomes unavoidable. The black hole is not just oversized, it is structurally disproportionate. The relationship between visible matter and central mass has shifted. And once that relationship shifts, every interpretation built on it begins to loosen. Growth, feedback, stability, all of it must be reconsidered under a new constraint. The system is no longer defined by balance, it is defined by excess. The first hard constraint appears when growth is traced backward. A black hole of this mass cannot form instantly. It must accumulate matter across long periods, drawing gas inward through gravitational capture. Time becomes the limiting factor. Even under ideal conditions, where gas flows steadily and radiation pressure is managed, there is a maximum rate at which a black hole can grow. This rate is set by the balance between gravity pulling matter inward and radiation pushing outward. Radiation pushes outward. This limit is not flexible. If too much matter falls in too quickly, the energy released drives material away, slowing further growth. This creates a natural ceiling. For most black holes, this ceiling ensures that growth remains tied to the evolution of the host galaxy. Gas supply, star formation, and feedback processes all regulate the rate. But this object exceeds what that ceiling would comfortably allow within the lifetime of its galaxy. This is the first rupture. Either the black hole began its life already massive, or it grew under conditions that bypassed the usual constraints. Both paths carry consequences. If it formed large, then the early universe must have allowed direct collapse events that produced extremely heavy seeds. Not small beginnings that gradually increased, but massive structures forming almost immediately. A star collapses and leaves a remnant. That is the usual path. But here, the required starting point is far beyond a stellar remnant. It implies a cloud of gas collapsing directly into a black hole without fragmenting into stars. A rare condition. The gas must remain hot enough to resist fragmentation, yet dense enough to collapse as a single structure. Radiation from nearby sources must suppress cooling, preventing the formation of smaller clumps. A narrow window of physics. If this occurred, then the black hole began already large, reducing the time needed to reach its current mass. But this explanation introduces a second constraint. Such events should be extremely rare, yet this object exists in a galaxy that is otherwise unremarkable. The host does not show signs of an extraordinary origin. The alternative is sustained growth under conditions that minimize feedback. Gas flows inward, but energy does not escape efficiently enough to halt the process. Accretion becomes hidden, energy trapped within dense flows, radiation unable to push outward effectively. The black hole feeds quietly. This scenario requires a specific geometry. Instead of a thin disk radiating energy freely, the inflow becomes thick, turbulent, optically dense. Photons scatter repeatedly, losing the ability to escape quickly. The energy remains contained. Matter continues to fall inward. A system like this can grow faster than the traditional limit would suggest. But it comes with visible consequences. Gas near the center becomes chaotic, temperatures rise unevenly, and radiation eventually leaks out in bursts. These signatures are not clearly present here. The system remains controlled, almost restrained. This deepens the tension. Every known growth path carries observable effects, yet the galaxy does not display them at the scale required. The black hole exists as evidence of a process that has left minimal trace. A hidden history. Now the conflict shifts from growth to containment. If the black hole reached this mass, then the surrounding galaxy had to endure the energy released during that process. Accretion converts mass into energy with high efficiency. A small fraction of infalling matter becomes radiation powerful enough to influence entire galaxies. That energy must go somewhere. Gas should be heated, outflows should emerge. Shock fronts should move through the interstellar medium. Imagine waves of energy pushing outward from the center, compressing some regions while evacuating others. Star formation should flicker, suppressed in some areas, triggered in others. The galaxy should carry the memory of this disturbance. Yet the structure remains relatively intact. Stars orbit in stable distributions. The system does not appear violently reshaped. This leads to a sharper realization. The constraint is not just about how the black hole grew, it is about how the system absorbed that growth without losing coherence. The galaxy acted as a container, but not a perfect one. Energy must have been redirected, dissipated, or confined in ways that prevented large-scale disruption. This suggests a deeper layer of structure. Perhaps the surrounding environment played a role. a larger halo of dark matter stabilizing the system, absorbing some of the energy through gravitational coupling. Perhaps inflows and outflows balanced over time, creating a dynamic equilibrium that prevented runaway effects. Or perhaps the growth occurred in phases, bursts separated by long periods of quiet, allowing the system to recover between events. Each possibility points to a system more complex than a simple galaxy black hole pair. The object is no longer just a black hole that is too large. It is the visible endpoint of a process that operated under hidden constraints. A process that managed to push against physical limits without triggering catastrophic failure. A quiet violation of expectation. And this is where the structure of the problem shifts again. The question is no longer confined to this galaxy. It expands outward. If one system can sustain this imbalance, others may exist. And if they do, then the rules governing black hole growth and galaxy evolution are not as tightly coupled as once believed. The ceiling did not break. It was bypassed. Growth alone does not explain the system. The next constraint emerges when stability is tested. A galaxy is not a passive container. It responds to mass, to energy, to imbalance. If a central black hole becomes too dominant, the surrounding structure should adjust. Orbits should distort. Velocity fields should shift. The entire system should reconfigure under the new gravitational hierarchy. Gravity reorganizes. To see this, imagine the galaxy not as a static image, but as a dynamic field of motion. Stars are not fixed points. They are trajectories, paths shaped by the distribution of mass beneath them. In a typical galaxy, the combined mass of stars and dark matter defines that field. The black hole influences only the inner region, a localized distortion within a larger structure. Here, that boundary is under pressure. The black hole extends its influence further outward than expected. Its gravitational pull contributes to motions that should be governed by the galaxy itself. This creates a layered instability. At small scales, stars near the center orbit rapidly, tightly bound to the black hole. At intermediate scales, the influence of the galaxy and the black hole begin to overlap. And in that overlap, the system must reconcile two sources of gravity that are no longer proportionate. This is where simple growth logic fails. If the black hole continues to dominate, it should begin to reshape the velocity distribution of stars across a wider region. Orbits would become more radial, less circular, stars diving toward the center and then swinging outward again. The system would heat dynamically. But the observations do not show a fully destabilized structure. Instead, the galaxy maintains a degree of order. Stars still follow coherent paths, not chaotic plunges. This implies a balancing force. Dark matter becomes part of the explanation. Surrounding the visible galaxy is a halo, a vast distribution of unseen mass that extends far beyond the luminous structure. This halo contributes to the gravitational field, smoothing out variations and providing stability across large distances. The halo absorbs imbalance. It acts as a buffer, distributing gravitational influence over a wider region, preventing the central mass from completely dominating the dynamics of the outer galaxy. This creates a containment layer. The black hole pushes outward in influence. The halo pulls the system back into equilibrium. Between them, the visible galaxy exists as an intermediate structure, shaped by both forces. This layered system allows the galaxy to remain intact even as its central mass exceeds expected limits. But this stability is not perfect. Subtle distortions appear. Velocity dispersions shift slightly higher than comparable galaxies. Orbital distributions hint at deeper gravitational potential. These are small signals, but they are consistent. They indicate that the system is under strain, not collapsing, but not entirely relaxed either. A quiet tension persists. Now consider the energy again. If the black hole grew through accretion, then energy was released in the process. That energy interacts with gas, heating it, pushing it, altering its distribution. In a system where the black hole dominates, this feedback should be strong. Gas near the center should be driven outward, reducing the fuel available for further growth. This is how many galaxies regulate themselves. But here, the regulation appears incomplete. Gas still exists within the galaxy, not entirely expelled, not entirely suppressed. Star formation has not been shut down completely. This suggests that feedback was either weaker than expected or more controlled. Energy may have escaped along narrow paths, jets, or channels that allowed it to leave the central region without disturbing the entire galaxy. A directional release. Imagine streams of high-energy particles moving along axes that avoid the dense regions of the galaxy. Energy leaves, but structure remains. This allows the black hole to grow without fully disrupting its host. Another possibility emerges. The growth of the black hole and the growth of the galaxy may have been decoupled in time. The black hole may have experienced rapid growth during an early phase when the galaxy was still forming. Later, the galaxy continued to evolve more slowly, adding stars without significantly increasing the central mass. This creates a temporal mismatch. The black hole reflects an earlier, more extreme phase of the system. The galaxy reflects a later, more stable period. Two histories layered into one structure. This would explain the imbalance. The black hole is a relic of conditions that no longer exist within the current galaxy, a memory of a more intense environment. But this explanation also carries a limit. If the black hole formed early and grew rapidly, then it should have influenced the formation of the galaxy that followed. Its gravitational pull and energy output would shape how gas collapsed into stars. The galaxy should bear that imprint. Yet the structure does not fully align with such an extreme influence. This returns the system to uncertainty. Every attempt to explain the imbalance introduces new constraints. Growth must occur, but without excessive feedback. Stability must be maintained, but under disproportionate gravity. History must align, but without clear evidence of extreme phases. The system holds together, but only just. This is not a failure of physics. It is a signal that the system operates within a wider structure that has not yet been fully accounted for. The galaxy is not isolated. Its stability may depend on forces and environments beyond its visible boundary. The imbalance is not contained within the galaxy alone. It extends outward. The system widens beyond the galaxy. The imbalance cannot be resolved within a single structure. A galaxy does not evolve alone. It exists inside a larger environment, a network of matter that spans millions of light years. This network defines supply. Gas does not appear inside galaxies without origin. It flows along filaments drawn by gravity into nodes where galaxies form and grow. These filaments act as channels. Cold gas streams inward from vast distances, feeding star formation and central black holes. The rate of this inflow determines how quickly a galaxy can build mass. Now the scale shifts. Imagine the galaxy not as a closed system, but as a junction within a larger web. Filaments stretch outward, connecting it to neighboring structures, guiding matter along invisible paths. The black hole may have tapped into this network more efficiently than the galaxy itself. This is the first widening. If gas flows preferentially toward the center, bypassing the outer regions where stars form, then the black hole can grow faster than the galaxy. A selective supply.
Streams of gas penetrate deep into the gravitational well, avoiding fragmentation, reaching the central region with minimal loss. Star formation remains moderate, but the black hole continues to gain mass. This creates divergence. The galaxy grows slowly. The black hole grows rapidly. Over time, the ratio breaks. This process depends on structure beyond the galaxy. The orientation of filaments, the density of surrounding matter, the motion of nearby systems, all influence how gas is delivered. A small change in alignment can redirect vast flows of matter. The galaxy becomes a gateway. Gas enters not uniformly, but along preferred directions, guided by the geometry of the cosmic web. In this scenario, the black hole is not an anomaly. It is the endpoint of an efficient supply chain. But this introduces a second expansion. The surrounding region must also be considered. Clusters and groups of galaxies create gravitational basins, regions where matter accumulates on even larger scales. Within these basins, flows can become more concentrated, feeding central systems more effectively. If this galaxy resides within such a basin, even a modest one, it may receive an enhanced supply of gas over long timescales. The black hole becomes the deepest point in a layered gravitational landscape. Matter falls inward from the web into the group, from the group into the galaxy, and from the galaxy into the black hole. A cascade of infall. Each layer funnels material toward the next. Now the imbalance takes on a different meaning. The black hole is not oversized relative to its immediate galaxy. It is scaled to a larger system that extends beyond what is visible. The galaxy appears too small, only because the full supply structure is not accounted for. This reframes the problem. Instead of asking why the black hole is too large, the question becomes whether the galaxy is only a partial representation of the system that feeds it. A hidden hierarchy emerges. At the smallest scale, stars orbit within the galaxy. At a larger scale, gas flows along filaments. At an even larger scale, gravitational basins organize entire regions of space. The black hole sits at the convergence of these layers. This is where the largest expansion occurs. Imagine a region of space spanning tens of millions of light years, where matter slowly drifts along curved paths defined by gravity. Galaxies are embedded within this flow, not isolated, but carried within a larger motion. The black hole becomes the final sink. Matter that begins its journey far beyond the galaxy eventually reaches the center, crossing scale after scale until it disappears into the event horizon. A continuous funnel. This perspective changes the interpretation of size. The black hole is not simply a feature of its galaxy, it is a node within a multi-scale system of accumulation. Its mass reflects not just local conditions, but the efficiency of transport across cosmic distances. This explains how it could grow beyond the limits expected from the galaxy alone. But it also introduces a new constraint. If the black hole is fed by such a system, then its growth is tied to the structure of the cosmic web itself. Changes in the environment, shifts in filament alignment, or interactions with neighboring galaxies could alter the supply. Growth becomes episodic. Periods of intense inflow followed by quiet phases where the supply weakens. The black hole grows in steps, not continuously. This pattern would leave subtle imprints. Variations in central activity, changes in gas distribution, shifts in star formation rates. The galaxy becomes a record of these cycles. Not all of them visible, but encoded in its structure. This is the deeper realization. The system cannot be understood by looking inward alone. Its defining feature, the oversized black hole, is a product of processes that operate across vast scales. The galaxy is not the container. It is one layer in a larger mechanism. And the black hole is where that mechanism converges. The meaning of the system shifts once more. It is no longer defined by how large the black hole is. It is defined by where the limits of containment begin to fail. A black hole of this scale does not simply sit at the center. It creates a boundary, a region where the rules governing matter, light, and motion are forced into extreme alignment. This boundary is not only the event horizon. It begins far outside it. The gravitational influence extends outward, shaping how gas approaches, how stars orbit, how energy moves through the system. There is a radius within which the black hole dictates behavior, and beyond which the galaxy reasserts control. In most systems, that radius is small. Here, it expands. The boundary grows outward, pushing against the internal structure of the galaxy, not violently, but persistently, redefining how matter is distributed and how motion is organized. The system becomes a layered boundary problem. Inside, gravity steepens rapidly, pulling matter inward along curved paths. Outside, the galaxy attempts to maintain its own equilibrium, distributing mass across wider orbits. Between them, a transition zone forms. This zone carries tension. Stars that enter it experience a shift in dominance, their orbits subtly altered as the central mass exerts stronger control. Gas moving through it begins to lose angular momentum, spiraling inward more efficiently than it would in a balanced system. Matter is redirected. This creates a slow migration. Over long timescales, material that once orbited safely at moderate distances drifts inward, feeding the central region. The black hole does not need to pull everything directly. It reshapes the pathways that lead to it. This is how influence becomes structure. Now consider the limit. If the black hole continues to dominate, this boundary will expand further. More of the galaxy will fall under its direct gravitational control. But the system cannot allow unlimited expansion. The dark matter halo, the surrounding environment, and the finite supply of gas impose constraints. At some point, the inflow weakens, the migration slows, and the boundary stabilizes. A balance forms again, but at a new scale. The galaxy adapts to the presence of an oversized center. It does not return to its original state. It reorganizes around a new dominant structure. This is the final shift in meaning. The black hole is not an object that failed to fit. It is a boundary that expanded until the system reclassified itself around it. The galaxy did not reject the imbalance. It absorbed it. Stars continue to orbit, but their motion now encodes a deeper gravitational hierarchy. Gas continues to flow, but its pathways are altered, guided toward the central sink with greater efficiency. The system remains stable, but only because its definition has changed. It is no longer a galaxy with a black hole. It is a gravitational structure whose central boundary has grown large enough to redefine everything inside it. A quiet transformation. And this reveals the underlying limit. There is no fixed proportion that must always hold. There is only a set of constraints, supply, feedback, environment, and containment that determine how far a system can stretch before it reorganizes. This system stretched further than expected. Not until it broke. Until it became something else. The black hole did not violate a rule. It revealed the boundary of one. What appeared to be an object that does not fit is in fact a system that was measured too narrowly. The expectation was built on local balance, galaxy and center growing together,
regulating each other through shared limits.
But that expectation assumed the system ended at the edge of the galaxy.
It does not. The measurements forced a wider frame, one that includes supply flowing across vast distances, containment provided by dark matter, and stability maintained through layered structures that extend far beyond visible stars. The black hole followed those deeper pathways. It grew where the system allowed it to grow. And when that growth exceeded the visible scale of the galaxy, the mismatch appeared not because the black hole was wrong, but because the frame was incomplete. Size became misleading. The object is not oversized. The system is underdescribed. This is the final reclassification. A galaxy is not the primary container of its central black hole. It is one layer within a larger gravitational network that feeds, stabilizes, and constrains growth across multiple scales. The black hole sits at the deepest point of that network. It measures the efficiency of everything above it. Gas flows, structural alignment, environmental density, all of it converges at a single location where matter crosses a final boundary. The event horizon is not where the story begins. It is where the measurement ends. Everything outside it determines what arrives there. This system shows what happens when that arrival is more efficient than expected. The center grows beyond the visible structure. The boundary expands. The galaxy adapts. Not by resisting, but by reorganizing around a deeper hierarchy of gravity. The result is not instability. It is a new equilibrium. A structure defined not by proportion, but by the limits of supply and containment across scales that extend far beyond what the eye can see. The black hole does not fit because it was never meant to be measured against the galaxy alone. It belongs to a larger architecture. And when that architecture is finally included, the imbalance resolves into something else. Not an error. A signal